So, good morning, everyone. I am Nathishkar together with Jenarththan and our mentors, Dr. Sathiparan, Dr. Daniel Nirban Subramaniam, and Dr. Pratibha Jeyananthan. Here we are to present our research topic on application of neural network for aggregate shape classification. So, let us have a brief introduction. So, aggregates are the coarse material used in civil construction ranging from 5 to 30 millimeter in size. And aggregates were subject to milling process in Los Angeles abbreviation machine where they get revolved for certain number of times known to be milling levels. The milling level will be selected based on the specific need of the construction. So when aggregates subject to milling process, their packing efficiency, interlocking ability and safety will be altered as the morphological and textural features of the aggregates get altered during the milling process. So let me discuss about our aim and objective. So here our aim is to improve the classification accuracy with varying degree of milling using convolutional neural network based transfer learning. So here our basic objective is to classify the aggregates into 6 milling classes. For that, we will utilize the pre-trained models such as ResNet 50 and EvisionNet B0 with transfer learning. And for the raw image sample, contrast limited adaptive histogram equalization will be applied to enhance the morphological features as a pre-processing technique. And the models will be evaluated based on the accuracy, precision, recall, and F1 score. So let me talk about our research gap and motivation for our research. So in previous studies, they have shown a good accuracy for the binary classification, whether it is milled or unmilled. But when it comes for the in terms of multi-class classification, that means classifying the aggregates within the milling level, their accuracies were extremely low. So here the multi-class classification accuracy is largely missing. So in our research, we will try to improvise the multi-class classification. And here, so far, they have no explored the CNN-based deep learning models for the aggregate shape classification. So here we will employ and see whether how it works for this particular domain. And in terms of aggregate shape classification, we need a robust, automated, and accurate approach to classify the aggregates across multiple milling levels. And CNN are extremely good at capturing the morphological and textural features rather than the handcrafted descriptors. So let us view our data pre-processing technique used in our research. So first of all, the raw data image was converted to the CLA-HE image where contrast limited adaptive histogram equalization happens. So here the raw data image is converted to the CLA-H image to enhance the morphological and textural features of the raw data set. Let me see our research methodology. So here we have converted the raw image into the CLA-H image, and this CLA-H image data set was used as a training data for the two pre-trained models known as ResNet 50 and EvisionNet B0. And these models were trained using the training dataset, and it is tested using the test dataset, which is kept unseen for these two models. And these results will be evaluated based on the accuracy, precision, recall, and F1 score. So here, let me view our dataset more detailedly. So here, totally we have totally 6 classes. For each class as a training data, we have 400 images as a training data and 100 images as a validation data. And for the testing data for each class, we have 2000 data. So totally as a training data, we have 2400 images and validation data 600 images and testing data 12,000 images. And totally we have 15,000 images for this research.
Thank you, Nathishkar. I am Jenarththan. Let's now talk about the implemented models and their performance. So far, we have implemented two state-of-the-art pre-trained model. One is ResNet 50, another one is EvisionNet V0. So these slides show the configuration of the ResNet 50 model where we use the pre-trained base from ImageNet with custom top layers, and we trained this model for 20 approaches with early stopping. In the figure, the training and validation accuracy is increasing and training and validation loss is decreasing. Which is confirming that model stable convergence without overfitting. And as you can see in the figure, the validation loss was started to increase, but this was controlled by early stopping that method that we have used. So let's talk about the ResNet 50 overall performance. So ResNet 50 model achieved an accuracy of 0.77 for 6-class classification. And the second table shows that the classification performance for each class. So now let's move on to the comparison of precision and recall for the different classes, which you can see in the figure. So the extreme classes such as 0, 100, 2000 have achieved high precision and recall. It's about zero point 0.9, while other intermediate classes such as 500, 1000, and 1500 show lower recall between 0.54 to 0.65, indicating that the model struggled uh, to separate these intermediate classes. So these confusion metrics show strong diagonal entries for the extreme classes such as 0, 100, and 2000, confirming correct prediction, while other intermediate classes show overlap, as you can see in that in those 9 blocks. So those are the misclassifications. So for an example, the class 500 was often misclassified as a 1000 or 1500 class. So that is all about the ResNet 50 model. So now let's move on to the efficient B node model. So this is the efficient B node model configuration. So efficient B node was tested under the same setup as ResNet 50 model. So the training and validation curve for the efficient B node were stable. So there is no overfitting identified. So this efficient B node model have achieved an accuracy of 0.72. This was slightly lower than the ResNet 50 model. So as you can see in the figure, the results are very similar to the ResNet 50 model. The extreme classes such as 0, 100, and 2000 perform really well, but the intermediate classes such as 500, 1000, and 1500 again showed confusion with recall dropping closer to 0.5 to 0.6. So the confusion matrix highlights the same problem. So overlap in intermediate milling classes, samples from classes like 500 and 1000 were often predicted as nearby categories, showing how hard it is to separate those classes, such as 500, 1000, and 1500. So let's move on to the results part. So in terms of the performance, ResNet 50 achieved 0.77 accuracy and EfficientNet B node reached 0.72 accuracy, both outperforming earlier shape-based methods that struggled around 0.6 for multi-class classification. And the key finding is that extreme classes like 0, 100, and 2000 were easy to classify, but the intermediate classes such as 500, 1000, and 1500 were much harder to distinguish. So, how the CNN is performing better in this multi-class classification is because the CLAG pre-processing improved feature visibility, and the pre-trained models like ResNet 50 and Efficient B node captured morphology and texture better than the prior methods. However, the limitation is that intermediate classes had very similar morphology, leading to overlap, and the backlight setup reduced the texture capture. For future improvement, we could fine-tune deeper CNN layers, use better lighting like dome lighting, or we can use 3D imaging as well.